You finish a job, and somewhere a program keeps running after its work is over. Nothing bad happens. The numbers stay inside the world that program expects. On the 4th of June 1996, the same arrangement destroyed a rocket in 39 seconds, and the reason is not the reason you have been told. The popular version of this story is one line of code. The inquiry board found the conversion error. Then it wrote that this in itself did not cause the mission to fail. That morning, Ariane 5 stood at Kourou for its maiden flight. The weather was acceptable, with no risk of lightning, but when the launch window opened, visibility did not meet the required criteria. The countdown stopped at 7 minutes before launch. The hold ended. At 9:33 and 59 seconds local time, the launch sequence began. The Vulcain main engine ignited. Both solid boosters ignited. Liftoff was nominal. For roughly the next 36 seconds, the flight remained nominal too. The rocket was accelerating along a trajectory unlike the one its guidance software had known before. Inside it, two computers were still performing a calculation that had once solved a real problem. On this vehicle, that calculation had no purpose at all. Just after that, the launcher veered. Its angle of attack passed 20 degrees. Aerodynamic loads rose until the solid boosters tore away from the core and the vehicle disintegrated. At 4 kilometers above the ground and 1 kilometer from the launch pad, self-destruction was automatically initiated upon disintegration as designed. The last telemetry reached the ground at 42 seconds. Debris fell across an area 5 kilometers long and 2.5 kilometers wide, nearly all mangrove swamp or savanna. Investigators recovered both inertial reference systems from that debris and used them in the analysis. Those units showed that the breakup was not the first failure. The rocket had already lost the information that told it how it was moving. Then its main computer acted on something that looked like flight data, but was not. To see the sequence, start with what an inertial reference system does. Laser gyroscopes sense rotation. Accelerometers sense motion. The system turns those measurements into guidance and attitude information, then sends that information across the data bus to the onboard computer. The onboard computer uses it to command the engine and booster nozzles. Ariane 5 carried 2 of these units running in parallel. One was active, the other was a hot standby, ready for the onboard computer to switch over when it detected a failure, provided that the other unit was functioning properly. This was redundancy against a unit failing at random. But the 2 boxes were identical in hardware and identical in software. They processed the same kind of data under the same flight conditions. A fault in one physical box could leave the other available. A design error shared by both could take them in sequence. That distinction became the whole mission. Deep inside the software was a variable called horizontal bias. It was related to the horizontal velocity sensed by the platform and calculated as an indicator of alignment precision over time. The software was written in Ada. One instruction converted this value from a 64-bit floating point number into a 16-bit signed integer. During the flight, the value no longer fitted inside the smaller format. The conversion raised an arithmetic exception when the value would not fit the destination type. That is the technical fact behind the one-line explanation, but it was not a stray typo. Engineers had analyzed the operations that could raise this exception. Other conversions of comparable variables in the same place in the code were protected. This conversion was not. The immediate cause was a number beyond a software limit. The important questions were why a pre-launch alignment value was still being calculated in flight, why its conversion was allowed to raise an exception, and what the system had been told to do when that exception arrived. Before launch, alignment gives the inertial platform a fixed, known position. After liftoff, it no longer means anything. The inquiry board wrote that as soon as the launcher lifts off, this function serves no purpose. Yet, flight mode began 3 seconds before launch, and the alignment function stayed active for 50 seconds after flight mode began. That kept it running for about 40 seconds of actual flight. The 50-second window came from an Ariane 4 launch requirement. If a countdown was held briefly, the launch could resume without repeating a normal alignment that took 45 minutes or more. This protected a short launch window. The feature was used exactly once in 1989 on Flight 33. For the new vehicle, that requirement did not apply. The function remained for commonality, based on the judgment that software which had worked well on its predecessor should not be changed unless change was proved necessary. But keeping alignment active in flight was self-defeating. Alignment assumes the launcher is fixed at a known position. Once the rocket moved, its real movement was interpreted as sensor offsets. A useful pre-launch function had become a source of meaningless values. It had produced meaningless values harmlessly for years, and became destructive only when the new trajectory pushed one past the old limit. On the earlier launcher's trajectory, this variable could not cross the software limit with an adequate operational margin. Its horizontal motion stayed inside the assumptions behind the conversion. The new vehicle crossed that boundary because Ariane 5 followed a different early trajectory. Its horizontal velocity built up 5 times more rapidly than its predecessors. The instruction had not changed. Its environment had. The same calculation met a different trajectory, and a value considered safely bounded was no longer bounded. The code was still familiar. The sky was not. When the value overflowed, the specification left no recovery path. Any exception had to flag the data bus, store the context in memory, and stop the processor. The backup unit failed first, at 36.7 seconds after the start of the main engine ignition sequence, approximately 30 seconds after liftoff. About 0.05 of a second later, the active unit failed for the same reason. Guidance and attitude information was no longer available. The inquiry board wrote that the identified source of the arithmetic exception did not by itself cause the mission to fail. It continued. It was the decision to cease the processor operation which finally proved fatal. Both computers were still healthy as equipment. Neither had suffered a random hardware failure. Each had encountered the same designed response to the same software exception. Identical software meant that one design error switched off 2 still healthy critical units. Redundancy had duplicated the hardware. It had also duplicated the decision. With guidance gone, the active inertial reference system sent essentially diagnostic information across the data bus. The main computer interpreted that information as flight data. On that basis, it commanded the booster nozzles and shortly afterwards the main engine nozzle to make a large correction for an attitude deviation that had not occurred. The rocket obeyed. Its nozzles moved hard in response to a false picture of its attitude. The earlier veer now had its cause. The angle of attack climbed beyond 20 degrees, and aerodynamic forces separated the boosters from the core. The number did not directly tear the rocket apart. The shutdown removed valid guidance. Diagnostic information replaced it. Then a functioning flight computer drove a real vehicle to correct a movement that existed only in the data. Behind the unprotected conversion was an explicit workload decision. The computer had a maximum workload target of 80%. Analysis identified 7 variables whose conversion could raise an arithmetic exception when a value would not fit the destination type. 4 variables received protection, and 3 variables received no protection. The 3 were judged either physically limited or protected by a large safety margin. For horizontal bias, that reasoning was faulty. The justification did not appear directly in the source code, and the agreed assumption was obscured, though not deliberately, from external review. More important, the project partners jointly agreed not to include the Ariane 5 trajectory data in the inertial reference system's requirements and specification. Without that trajectory as a functional requirement, no test was defined to run the real unit through the Ariane 5 countdown, flight sequence, and predicted motion. The equipment testing itself was rigorous. In places, it went beyond what Ariane 5 required. A ground test with simulated accelerometer signals and a turntable was feasible, and the board wrote that it would have exposed the failure mechanism. The real inertial reference systems were also absent from the closed-loop system simulations. Software models replaced them. The reasons for that choice were technically valid, but the board found a definite risk in assuming that critical equipment had already been validated on its own, or through Ariane 4. Its finding was direct. Had the system been included, the failure could have been detected. The missing test was not skipped. It was never defined by the requirements. At the end, the inquiry board traced the response to a program culture focused on random hardware failures. This exception was not random. It was a design error. The prevailing view had treated software as correct until shown to be at fault. The board recommended the opposite. Software should be assumed to be faulty until it has been demonstrated that it is correct. That is the difference between a spare computer and an independent defense. Ariane 5 had two healthy boxes, but both carried the same assumptions, the same limit, and the same command to stop. You finish a job, and a program keeps running. Usually nothing happens. Here the old function met a new sky, and the process that had finished its work shut down the computers that the rocket still needed.